So thank you everybody for joining. We are very happy to have with us today Joana Kramer from Los Alamos. Joana did her undergraduate and master at the University of Bonn, and then continued with a PhD in the sort of adjacent institute of the Max Planck for radio astronomy. She specializes on RMHD simulations of jets, and she's among the very few people in the world that can do actual full RMHD polarization simulations and data analysis, which I'm guessing there'll be a combination of the two, judging just from the title. But yeah, Joana is also a member of PhD, M2 Finers, and she's going to be here with us today. So if you guys are interested generally in simulations, VLBI, or anything related, this is the time for you to grab it. So, Joana, thank you very much for coming.
Thank you, Janis. Thank you, everyone, for coming. Thank you for having me and allowing me to give a seminar talk and allowing me to extend my stay in Greece. I'm going to talk about observations to simulations, as Janis mentioned, and I'm going to talk about several AGN jets, and I will explain everything along the way, what an AGN, for example, actually means. So if we're going to start with one of the most famous AGNs, Messier 87, M87, which is one of the black hole jets and the black hole that has been imaged for the first time by the Event Horizon Telescope Corporation, but let's go in history sample. So in 1918, there was the first optical UV jet discovery in M87. Then in 1954, the term jet was introduced for the first time. In 1999, the jet was found highly polarized and with an automatic field. Then in 2019, the Event Horizon Telescope Corporation imaged for the first time a black hole event horizon or black hole shadow. And in 2023, which we've seen just right there, GMVA observations revealed a disjet connection with this three-finger image you might have seen. And I'm part of the, as Janis mentioned, I'm part of the Event Horizon Telescope Collaboration. So I'm very interested in AGN jets, but also in other jets in the universe. So in this talk, I'm going to talk about relativistic jets, about observations in the radio regime, mostly, and then about simulations and radiative transfer. So how to go from simulations to actually light that we can observe, for example, synchrotron emission. And what combines all of these topics? Well, that's me. So that's why I'm here, and that's what I'm going to talk about today. For the history of AGN, there are several catalogs you can look up online, several data banks, several observations that are for the public as well. So you can make use of all of those, which are great. So thanks to all of the previous observers throughout the centuries. But as my title said, I'm going to focus on our favorite AGNs. One of them is 3C84. One of the sources I published with my collaborators as well. And then another one is BL-LUC, which I'm working on currently with Janis. So I'm going to talk about how I bridge my simulations to those observations later in the talk. The main question is, how does the polarized synchrotron emission in AGN jets depend on the intrinsic magnetic field morphology? Does it depend on it at all? Can we distinguish it and all of that? So we're going to answer this in this talk. Let's start now with an AGN. What is an active galactic nuclei? There's a famous unification model, which assumes that you have a supermassive black hole situated in the center, surrounded by an accretion flow, accretion disk, maybe a torus as well. You have a disk-jet boundary, and you have a relativistic jet. Within this, you might have several winds, radiative structures, but also different jet launching mechanisms, the Blandford and Snark and Blandford and Payne mechanisms. I'm not going to talk about those, but I'm happy to answer questions about those later. if you zoom out, you might have a dusty torus, and you have narrow and borderline regions within those, so we can observe spectral lines and distinguish different AGN types. I'm also not going to talk about that, but happy to answer questions if I can. Then further out, you might have now the spectrum dominated by the relatively big jet. But what distinguishes an active galactic nuclei from a normal galaxy is that it is orders of magnitude, several orders of magnitudes brighter than normal galaxies. And in the AGN population, only like 10% are radio loud sources, which means they have a radio jet. Further, AGNs can be distinguished by their radio loudness, so basically the jet strength, the Eddington ratio, and the inclination. The inclination means that we have a system and we have the galaxy in the sky and we observe it from a certain degree. So if you would have a radio galaxy, you would see the galaxy edge on, and you would see the jets emanating away from the center black hole. If you have a blazar source, you're assuming that you're looking right into the jet itself. I'm going to talk about both radio galaxies in my simulations and also blazars in my simulations. Why can we observe it from every angle? That's because it's synchrotron radiation. And in synchrotron radiation, you have electrons spiraling around magnetic field lines, and those emit along the way as they spiral around the magnetic field lines. So you have light in every direction. Now, if you focus on the jet and the features in the jet, you can have different magnetic field structures, helixes, you can have blobs moving in the jet, here in red, or you can have recollimation shocks or standing features here in the blue cross. And a typical spectrum is shown here, which shows the power over the frequency, and you have a certain turnover frequency where you go from the optically thick regime to the optically thin regime. For my part, we are focusing on the optically thin regime, where you have a certain power law and radiative losses, so a power law cutoff. And the power law is related to the electron energy distribution. So in observations, you can have the spectral index by overlapping two frequencies, whereas for the theoretical part of it, you can assume electrons, and electrons have a certain power law, energy distribution, and those are connected, which is very important and makes it easy for us to interpret. So we're going to focus my work and all of this talk on the non-thermal synchrotron emission of AGN jets. To understand that further, as Janus mentioned as well, we have to understand polarization. Polarization can be defined by the Stokes parameters, I, Q, U, and V, which are basically mathematical functions of the electric vector. Stokes I would be the total intensity, Q and U the linearly polarized intensity, and Stokes V is the circular polarization. Further, we can define the EVPA, electric vector position angle, which is an equation based on the Stokes U and Q vector, so the linear polarization in principle. And in the optically thin regime, we assume that it's perpendicular to the magnetic field. So if we can observe the EVPAs, we can infer the magnetic field structure from it. This basically can be summarized in this figure. You might have an electric vector plane. You might have some rotating medium also along the way of your observations, which can cause to rotate your polarization. And then you can observe either like linearly polarized light in the 90 degrees or 45-degree direction, or circular polarized light, which rotates around the plane. And why is circular polarization so important in my view is because you can get insights on magnetic field orientations, but also on the plasma composition. Some of you attended the conference last week, and there was a question on Friday in the final session, how we best observe polarization. I was like one of 4 people who selected circular polarization out of 100. I stand with that. So we talked about relativistic jets, we talked about AGN and catalogs, and now we're going to talk about observations. So just to dive into some history as well, back in the 60s, 70s, or back in the last century in general, there was a single dish area with radio telescopes, and they managed to image AGN jets at kiloparsec scales. They established flux densities, observed spectra, and helped with the AGN classification. Then later we have the VLBI era, very long baseline interferometry, which resolved fine jet structures, and the black hole, which we observed in M87, also revealed shocks or not standing features. And we did have at some point space VLBI, radio astron, and then proposals for new space missions as well these days. The great thing about radio astronomy is you actually have amazing sites you can visit. Radio astronomy in general can be boring, in my view. You don't have these beautiful, colorful images like the optical, but radio astronomy can be really cool, and you can visit the sites. You can also climb the dishes, which is pretty cool as well. And I just want to mention there's one VLBI site in New Mexico, close by where I live, which is very nice as well. So then, how does interferometry work? So for VLBI, we have telescopes on different parts of the Earth, and we basically make use of the rotation of the Earth and use the Earth as a telescope itself. So we have a pair of telescopes which corresponds to a baseline, so the distance between two telescope sites. Then the array produces a sparse sample in the Fourier domain, which you can see here. So each telescope pair creates one data point. And then the Fourier domain is filled out as the Earth rotates. That's how we observe the black hole image or features in the jet. The very long baseline array, one of the specific VLBI arrays we have, consists of 10 antennas of each 25-meter dishes in the radio regime, between 0.3 to 96 gigahertz. It has a great resolution and a very long baseline. So the furthest telescope sites are about 8,000 kilometers apart. We need VLBI for several things. We need to increase resolution, which we do get by increasing the number of telescopes and the distance, and also by changing the frequencies. So higher frequencies allow us to look deeper. On the other hand, we also need small and large telescopes. So a good combination of smaller and larger antennas in your array would be favored. For my study, I selected 18 sources. 9 sources out of those are blazar sources that showed high polarization in the past with the VLBA. I observed those 9 sources in 2 frequencies, 15 and 23 gigahertz. And then from there, worked on the data, which means that I corrected for the parallactic angle and Earth rotation, as I mentioned how the principle works. Applied fringe fitting and opacity corrections for the frequencies, solved for group delay and polarization, and leakage terms. And then for my method, I created clean images as a base, but then we applied actually regularly maximum likelihood measurements or techniques with the docket software.
What are there in the X and Y axis in this box?
It's basically the distance between telescopes. In the UV domain, it's a Fourier domain. Each data point collects an intensity based on the location of the telescopes. So if telescopes are closer together, I think you get sparse samples or sparse points around the edges. If they're further away, you get more samples in the center, and you need both of them to create a full UV domain, a full image of data points that you can then later Fourier transform into actual intensity maps. Okay, I'm going to show my observations later, but that's basically the theory for it. So let's talk about the theory for simulations and the radiative transfer. So for large-scale jets, you need special relativistic magnetohydrodynamic simulations. They focus on the plasma flows, and they have features like the recollimation shocks, knots, intensity, and in my case, polarization as well in the radiative transfer calculations. So you apply post-process ray tracing to extract the emission and relativistic outflows or effects. On the other hand, you can have microphysics, which are mostly applied in particle and cell simulations, but I'm not applying particle and cell, but a hybrid model. That means I have some microphysics, which helps to include physical processes like synchrotron cooling. That means that you already have non-thermal particles included in your simulations, which will be important, and I mention later why. All of this sounds very abstract, but we can actually see it on the Earth or like close by as well, on actual jets, fighter jets, planes, whatever. You can see those recollimation shocks, for example, in the airflow behind a fighter jet. And that's the same principle. It's just hydrodynamics, it's plasma physics, it's applicable to processes on Earth as well. Also to fusion, for example. Okay, for the jet simulation setup, it looks like this. I'm applying the Pluto code in purely thermal variables. I have a three-dimensional box. I have a jet nozzle, which is just assuming a radius with you assume a pre-existing jet, you assume a radius, and you just shoot plasma into the radius, into the three-dimensional box. You can see the jet stream moving from top to bottom or bottom to top in other figures, but let's say from top to bottom. It's relativistic magnetohydrodynamics, so I'm including hydrodynamics, but also the magnetic field, which means that my set of equations for the conservative laws are dependent on the density, the pressure, the magnetic field, and the velocity. And then it's, as I said, three-dimensional. It can be adjusted to any size, but an average size I use is like 360 times 400 times 360 cells. And this is all in non-dimensional units, so you have to apply some physical units to it. In my case, I chose one cell size to be 1 parsec, the speed of light as normalization for the velocity, and then some density normalization for the ambient medium. So this looks then like this. You have an underdense jet moving in a dense medium from top to bottom. This is a 2D cut out of the three-dimensional simulation. You have a jet nozzle, a jet radius, and you can see that several features are building throughout the simulation. For example, you can see reclamation shock or standing shock right there. And that's basically what we're going to observe and study. So in the first study, the magnetic field morphology study, I'm going to mention throughout the talk again and again, is that we can have two very different magnetic field morphologies, the poloidal and the toroidal case. So for the poloidal case on top, you have magnetic field lines streaming with the jet stream. For the toroidal case, you have magnetic field lines spiraling around the jet stream itself. And you can have a mixture of both, but you can have those two extreme cases. So can polarization help to distinguish underlying physics? By looking at this, I would say yes. That's a first guess, and I'm going to go into more details of my results later. But how do I get there? This is by applying the Pluto code now, focusing on the relativistic, focusing on the reclamation shock. But as I said, the Pluto simulation is purely thermal, so density, pressure, magnetic field, velocity. However, emission, observed emission, synchrotron emission in particular is non-thermal. So how do we go from thermal variables to non-thermal emission? This is by applying, for example, one example that we did, applying proportionalities between the thermal variables to the non-thermal electron energy distribution. So you can solve those two integrals for two unknowns. And those two unknowns are the normalization of the electron energy distribution and the minimum Lorentz factor of the electrons, so the minimum energy of the electrons. And as I said earlier, the power law index of the electron energy distribution is then again related to the spectral index, which is a powerful tool to observe or in observations.
So this is a jet with electrons, not protons, right?
Yes.
So you allow electrons to go in. That's what you do, right? Okay, you assume these are electrons.
It's
And then in the
painted.
nozzle, they just have one velocity. That's what you assume.
Yes.
Okay.
Yeah.
And what do we see here? What are the colors?
So that's density on the left.
Density.
Yeah,
Right.
that's density in thermal variables, and then you just paint electrons on top of it. Intrinsically in this
That's
set,
density of electrons. That's what we see.
no, that's just density of the plasma of a thermal
And-
flow.
Plasma or what?
It's just a thermal flow. You just assume a density for the ambient medium, a homogeneous ambient medium, and an underdense jet streaming through it, just in the equations of hydrodynamics.
So the blue one, the middle is the density of electrons rejected.
This one or this
No,
one?
this.
That's just the underdense jet forming a recollimation shock, so forming plasma to collide. And the blue, the blue is the jet center. Then this yellowish region is backflowing material, and the orange region is a homogeneous ambient medium. And you have the bow shock here in red, which is all thermal. And then you just paint electrons on top of it. There are no electrons intrinsically in the simulation, in that case specifically. So you just paint electrons on top of it by assuming, well, by having the electron energy distribution here in this case, proportional to the density. You solve for the density, and in certain density regions, you just assume there are like X amount of electrons with X energy. So you do that and you get to a synthetic synchrotron emission in non-thermal values. Here in Stokes I, so total intensity, in that case in 86 gigahertz and in radio frequencies. And it is calculated based on the Stokes parameters. So you basically calculate the radiative transfer, again, based on the magnetic field, the energy, the electron energy distribution, and then you can add effects like Faraday rotation and Faraday conversion as well. So all of this is integrated into our radiative transfer calculations. So this view is basically, as I said, the jet is moving from top to bottom. We are looking edge on the jet, which means it's basically like a radio galaxy. But it's a three-dimensional simulation. So we can rotate our simulation and have a more blazar-like view. We can do that, and then we can also solve for circular polarization, since we do have a full set of Stokes parameters, I, Q, U, and V. So we can solve for circular polarization, which would look like that. But for my results, we can go into more details. A second. So from top to bottom, we can see here a poloidal field, a helical field, and a toroidal field. From left to right, we have total intensity, linearly polarized intensity overplotted with EVPAs, and circular polarization. And we can see that, for example, for the poloidal magnetic field, we can see a dominance by the jet spine or the recollimation shock, which we assume with the radio core in observations. For the toroidal field, we can see an edge Bryson polarized emission or an edge Bryson total intensity. We can also see a bimodal pattern in the EVPAs. It's hard to tell, but along the jet, the EVPAs are oriented with the jet, and on the edges, they are perpendicular to the jet. And we have two signs in circular polarization. We have a negative and a positive circular polarization. on the two different edges of the jet. That means, based on this, resolved linear and circular polarization imaging of radio galaxies can already distinguish between different underlying physics. In this case, underlying magnetic field configurations. And then we do the same. We rotate it to a blazar-like view. So in this case, we can see different features again. I just want to stress that we have two signs in circular polarization. So polarized emission from lasers can also hint towards a favorable magnetic field. So then we have the set of simulated images, which we now want to compare to observations. So as I said earlier, we have now our prior images with the clean algorithm, with the clean technique, which we then put into DocKit. This whole procedure is distinguished from what has done in the past in the usually applied method by Dan Homan and Lister with the clean, with the clean algorithm. But now we add some iterations and some techniques to apply DocKit, so regularly maximum likelihood, which is less biased by humans. The most important features are that we apply faceless self-calibration. We integrate Stokes V. We don't assume that it's zero, but we actually integrate it. We combine GPCal, so leakage terms, with DocKit D terms. And we have fidelity-based gain transfer to improve reliability. Sorry. This looks then like this. So 9 of our sources are not very famous sources, just 9 sources we picked with high polarization, image with DocKit, self-calibration with closure only, assuming that the Stokes I is always, so the total intensity is always brighter than polarization, and we include the circular polarization as well. And we have that in 2 frequencies, so 15 gigahertz and 23 gigahertz, which shows a robustness of the EVPA over epochs and frequencies. Over epochs, because we compare it to the Mojave sample, the Mojave database over the last years or decades even. We have that in circular polarization as well, in 15 and 23 gigahertz. And by comparing it to my simulations, we can, for example, see see 2 signs in circular polarization, which means that we can reveal a favored underlying magnetic field and the possibility of opacity changes as we look from 15 to 23 gigahertz. And then finally, we can actually apply our simulations to specific sources. In this case, for example, the radio galaxy Centaurus A. On the left, you can see observations in brightness temperature by autonomy and the HT. And you can see the edge brightened jet. So we try to reproduce the edge brightening for Centaurus A. We applied 86 gigahertz, an orientation of or inclination of 35 degrees, and a Lorentz factor of 7, Bike Lorentz factor. And we managed to represent the edge brightened jet here in linearly polarized light. We also have EVPAs in my simulations, the whole polarization in principle. Unfortunately, there are no polarized observations of Centaurus A yet. We keep proposing for it, but we keep getting rejected. So let's hope this cycle we might get it or not. But what we've seen in this case for Centaurus A is if we go from lower frequencies to higher frequencies, so 1 gigahertz, 15 gigahertz, 86 gigahertz, and 230 gigahertz, we move the emission closer to the jet nozzle region. So you could say closer to the black hole, even though we don't consider the black hole at all, but we move the emission closer to the core, closer to the region of injection, which we discussed and interpret as the core shift. So you see in the core shift is basically that you see in different frequencies the radio core at different positions in the jet, depending on the frequency. So for lower frequencies, you see it further out. For higher frequencies, you can see the radio core further in, closer to the black hole, assumed black hole. That's a study for Centaurus A. For 3C84, we had radio observations in 22 gigahertz here on the left. Here also in polarization, and we see a bimodal pattern and edge brightening in polarization. So we tried to reproduce that, and we managed. So first of all, we can see here in linear polarized light simulated the jet bending. We can see EBPAs with a bimodal pattern, and we can investigate different magnetic field structures and how we get there. So for 3C84, we looked at different magnetic fields and different Lorentz factors. So here on top, you have 3 different magnetic fields. So you have the toroidal magnetic field, a helical magnetic field, and a poloidal magnetic field. And then on bottom, we investigated different Lorentz factors. So in all of these, on top, you have a bike Lorentz factor of 1, and then you have a bike Lorentz factor of 3 and 7. And as I've shown on the previous slide, we confirmed that in our case, what we assume in my simulations is that a Lorentz factor of 1 and an underlying toroidal magnetic field can reproduce the jet bending and the polarized observational features in 3C84. And then finally, just very preliminary results with Janis and George on BLAC. We try to reproduce the polarization degree and angle in 2 different radio frequencies, also in the optical, but in my case, in the 2 different radio frequencies, which we assume, based on the observations, to be a variation or a precessing jet, a varying jet, a moving jet, something like that. So we try to apply my simulations, vary the inclination, make the jet moving. It's not a time study, but it's at least based on the different jet inclinations and where the jet is oriented to study the EVPA, to study the degree, well, the polarization angle and degree, and compare it to the variability in BLAC. This study is based on the inclination, on the magnetic field, but also, just as we found out last week, on plasma composition. So the ratio between positrons and protons assumed in the radiative transfer calculations. So finally, for the mystery of active galactic nuclei, we questioned the magnetic field structure. So we had a look at the polarized synchrotron emission of AGN jets in observations and simulations. That means we applied simulations with a variant input deck. So the jet nozzle size, magnetic field, Lorentz factor, distance, inclination, we can change all of those. And we can apply it to observations. And we found a consistent spine sheath geometry with a mild relativistic flow. We saw a limb brightening or edge brightening for a toroidal magnetic field. And we saw a consistency in poloid magnetic fields enforcing recollimation shocks or the highlighting of the central spine. And then finally, we identified magnetic field configurations for various galaxies, blazars, as well as binary sources. Thank you.
Any questions? Please.
have many, so stop me.
Well, how many do you have?
2.
Oh my
I
God.
have 22. Go.
Okay. So, first, back on your slide 26, 27, something like that, you show us the simulation. Yes, here. Okay, so I understood from your simulation at the beginning that when I was seeing something like the top left
Mhm.
image,
Yeah.
that was like the typical morphology of recollimation shock. Total intensity when you have this type of X-shaped structure, or am I very much so? This you don't have a recollimation shock, is it? What?
It is the recollimation shock, but I don't have a figure of that. It's, let me go back to. So yeah, in the underlying fluid simulation, you form a recollimation shock, both for the polaroidal and toroidal case, but it's stronger for the fluid, for the polaroidal case. So if the magnetic field lines are streaming with the jet stream. And then, but still you have, in both cases, you have recollimation shocks in the fluid. But then if you apply the radiative transfer calculations, which are based on the magnetic field, and since you have a rotating magnetic field for the toroidal case, you don't see the recollimation shock anymore. But for the polaroidal case, you still see the recollimation shock just highlighted in synchrotron emission.
Your simulation are telling us that if from an observational observer perspective, if I don't see something that I would call a recollimation shock, with typical, I may say that we have then a colloidal, a dominant colloidal magnetic field at sorry, if I don't see a dominant toroidal at a larger scale. Yeah. Okay, that's interesting. But I haven't seen it yet in other simulations. It's kind of interesting. Okay, this was one, thanks.
Yeah.
For Centaurus A, so you told us about 3C84, so the comparison of your simulation with the data, you told us that you have a preference for the toroidal magnetic field there. Yeah. Can you say us something about the preference?
For Centaurus A?
Yeah.
Yeah, for Centaurus A, since it's the edge brightening, it's also mainly reproduced by the toroidal case. Yeah. Yeah.
Third week, thanks. The circular polarization in your model comes from intrinsic, not Faraday version?
No, intrinsic.
Intrinsic.
Yeah. We have some effects of Faraday conversion on rotation, but it's applied. The calculations are based on the intrinsic fluid stream.
Yeah. Yes.
Okay, then that was rather quick. But I wanted to ask a very cool results, by the way, is like these when you showed the polarization observations of like a number of AGN jets, like how was the sample like selected? Do you have a preference for like if it's a fuse, be a lax, for example, there, or you could select them from the highest polarization in Mojave survey or something like that?
More or less, the latter case. So we wanted to have blazar sources. We picked 18 sources, 9 calibrator sources, and 9 sample sources, all blazars. And we just checked the whole Mojave, more or less the whole Mojave sample, and picked 9 blazars with the highest, almost highest polarization. So we were kind of sure we would observe polarization again. And then we wanted to compare it to the previous epochs, so to the whole Mojave archive, based on the 9 sources we selected.
So you selected them to have higher linear polarization, so you have also higher chance to detect circular polarization, which has not been observed before.
Circular polarization has been observed. So if you go to the Mojave website, you can also see circular polarization degrees for some of the sources. Yeah.
Okay, and then like for the results that you see, for how many sources do you see like a significant like bimodal pattern that you were seeing showing in the simulations.
Yeah.
That it was clearly like showing like true.
Not too many because of the blazar sources, which rarely show any jet structure. So the EVPA structure, the bimodal EVPA structure would be in my simulations mostly in the jet. So for 1127, we're basically the middle row, but also for 0149 plus 218. If you see a jet, we might have observed bimodal EVPA pattern as well. Maybe let's say for like 2 out of the sources. I would have to check the paper again, but
It's circular polarization. That's what I was curious about.
yeah.
Because I could see that some of them seem to show that, which was really cool.
Yes, they do. We finalized the images some more. So again, I would advise you to check the paper, or we can check it after together. There's also a table in the paper which basically says or tells you our idea of the favored magnetic field for the core and the jet, depending on the source. But yeah, we do see some features which we think would be ideal for toroidal case. And we do have one course which really only show like one polarization, like in this case, where you only have a negative circular polarization.
I have one more question, if I might.
Sure.
It's a third one.
But I thought
Please go ahead.
all in my head, I thought these
Go
was
ahead.
one question.
Go ahead.
Yeah, so we were showing the results from like the modeling of BC84. Like which actually look really like pretty much like the source.
Right.
I was wondering if you input this I mean if you input like a straight jet with toroidal magnetic field, like how can you then like even if you change the viewing angle, like overall viewing angle, how do you produce this jet band?
Because I didn't show in any earlier movies, that the jet here has a lower Lorentz factor. So in all of the slides before that, and the movies you've seen and the jet stream, I assumed a Lorentz factor of 7. And then in this case, that was the first instance I changed it to 1. And the jet basically slows down and starts to wiggle or bend into one direction. So it starts to be disruptive at some point. And that's how we basically managed to have a jet bending.
Was actually the result of instabilities on the simulator.
Yeah.
Oh, very good. Thank you. That was all for me, I think.
Okay. Any more questions?
Yeah, I'm not an expert. How does it work exactly, the painting of the electrons? So how do you connect this part with the particle acceleration, which is strongly related then to what you see?
Yeah. In every single cell, you have a certain density and a certain pressure. And you have these two equations, and as you have a set of 2 equations in math and a set of 2 unknowns, you just solve these 2 equations together, have the input of the density and pressure in each cell, solve for the normalization and the lower energy cutoff of the electrons, and just by that, having a certain value in each cell, that will give you then the electron distribution, basically.
So you are assuming the gamma maps or?
Yeah.
Okay.
In that case, we had a fixed. No, in that case, yeah, you assume a gamma max. You can also have a third equation, so a third proportionality of the electron energy distribution to the magnetic field. So density, pressure, and magnetic field. So you have 3 equations. And then you can also fix the gamma min and gamma max or solve for it based on how many equations you have that way around. But you always assume basically a maximum Lorentz factor. Unless in a hybrid approach, which I didn't show here because I didn't know if I would have time. But now we have, well, actually, let me show you, maybe. Oh, yeah. So what you can do now is have a Lagrangian particle population following the fluid stream. And all of those already have an electron energy distribution. So it solves it while simulating simultaneously to the jet flow. And then you don't have to do the painting anymore and solve in every cell, but you actually have it all stored in the Lagrangian particle parameters.